Now that we have looked at how to write validators low level, where all three arguments to the validator function are just built-in data, we want to look at the typed version. And why would you want a typed version? Well, to always just use built-in data feels a lot like working in an untyped language like JavaScript or Python. So you, in particular, can represent values of this type that have nothing to do with your business logic, that shouldn't be representable really. For example, in our case, the redeemer, the idea is basically the IDEMA should be an integer, but we have all these other constructors in built-in data as well, like lists and byte strings and so on. And often that's far too much, and you want to have types that much better reflect your business logic. And this is especially bad for the third argument, the context, which contains the transaction and its inputs and outputs. I mean, because even though you certainly can imagine how one can encode something like a transaction with its inputs and outputs in this built-in data type, it's not at all clear how exactly the encoding works. So it's quite difficult to get to the pieces of information you actually want to look at. So it's much more convenient if we have strong types that are much better suited to the case, to the business case we are working on. So it's nicer to use this type version that I'm going to show you now. But as I mentioned before, it also comes with performance impact, resource impact. So the compiled Plutus core scripts become bigger, and the number of execution steps needed to execute the validator and the memory consumption, they go up. So if resources are tight, you might want to actually use the low-level version. But at least for learning Plutus, I think it's much nicer to look at the typed version that I'm going to show you now. And the idea is, in principle, you can use more or less arbitrary types for datum and redeemer. So in our case, we don't really care about the datum, so an appropriate choice here would be to just use the unit type. And for redeemer, let's use integer. And this third argument, there is a type called script context, which is much easier to work with than with this blob type, this JSON-like type built-in data. Okay, so, and in this case, the final change to the untyped version, to the low-level version, is that we no longer have a unit return type, but the much more natural feeling bool. So the idea is, if the validator, this typed validator, returns true, then validation is okay, and if it returns false, it's not. However, you can still, as before, throw errors as well. So validation fails if the function returns false or if there is an error. Okay, and if we do that, then this dramatically simplifies. So we don't need these two cases, so we can just express this as r equals 42. So this looks much nicer. If we did it like this, however, we would have the same problem as before. So if somebody provides a redeemer that is not 42, then we would just get a script failure, and it would be hard to debug or hard to find out why validation failed. I mean, obviously not in a simple case like this, but you can imagine if you have much more complex validation logic and something goes wrong and you just see something went wrong, it's very hard to actually track down why the transaction didn't validate. And in the low-level case, we use this trace error function to give some debug information, some tracing information. And in the typed version, there's another nice function that's called trace if false. Wrong redeemer. Let's first see whether it compiles. It does. And now we can look at the type of that, this trace if false. Trace if false. So we see it takes two arguments, a string, a Plutus string, and a Boolean. So the semantics of this is, if this Boolean is true, then the string, the first argument, is ignored and the function returns true. If, however, the second argument is false, then the function will return false, but the string will be locked or traced. So in this case, if the redeemer is 42, then validation passes, we just get true, but if it's not, then not only will the function return false, in addition to that, we also will get this error message. Now that we have written our validator in Haskell, we of course again need to compile it to Plutus Core. And this unfortunately requires some more boilerplate now than in the untyped case. So let's look at that. I pasted the relevant code in here. So all of this is boilerplate more or less. First of all, we need something that we didn't have before. We need to introduce a new type that encodes the information about the type of the datum and the redeemer. So we can pick an arbitrary name for this type. I just called it typed. And it doesn't need any constructors. You will never actually need a value of this type. The type is just needed to then provide an instance of the class scripts.validator types for this new type. And by the way, the scripts now comes from ledger.typed.scripts. So now we are using the typed version of the scripts. And what this class does is it basically just records, as I said, the datum and the redeemer type. So it uses these type instances. So we just say, okay, the datum type is unit because we decided to use unit for our datum, and the redeemer type is integer because we decided to use integer. So that's the first thing. You need to introduce this data type and then write an instance of the validator types class to record datum and redeemer type. And then to do the actual compilation, there's also something in the scripts module called make type validator. And you have to tell it that you're using it at this typed type. This line here is as before, so we take our validator and use plutus.txt.compile to compile it. But this now has the wrong type. Remember, I mean, eventually we need something of this low-level type, build data to build data to build data to unit. So we need some sort of translation between the strong types and the low-level version. And this is done by this wrap function, which you don't have to write by hand. That is also provided in the scripts module. So you can always use wrapped as wrap validator, and you again have to tell it which types to use there for datum and redeemer. So this is more complicated, more to write, but as before, it will always be the same. So whenever you want to use this typed version of Plutus, you can more or less just copy paste from, for example, this example, and then adapt it to the types and the names that you are using. And then once we have this typed validator, we can, as before, get a validator hash, and an address from that. So first we can get an untyped validator using the validator script function. We can use a typed version of function validator hash to turn this typed validator into a validator hash. And as before, having the untyped validator, we can use script address to actually get an address. If you want, we can try that out in the REPL. So this val hash and the script address. Right. So the advantage is that you can write your business logic much more concisely. You don't have to worry about how to encode your data in this built-in data type. We haven't looked at actually uses for the script context yet, but once we do, you'll see that it's much more convenient to have the script context type instead of having to deal with raw, untyped built-in data. But the price is that your scripts will be bigger and need more execution steps and more memory, and you have to write this additional boilerplate in order to actually compile it. Now let's briefly look at the off-chain code. This is almost identical to the untyped version. There's one difference here in this line. Earlier we had something called must pay to other script, and now it's must pay to the script. So this is a typed version, a convenience function for the common case that your off-chain code or the transaction you are constructing in your off-chain code only involves one script. Doesn't necessarily have to be the case. Of course, a transaction can take inputs from different script addresses and produce outputs to various script addresses. But it's quite common that there's only one script involved in a transaction. And in that case, you can use this must pay to the script. Actually, you can also use it when there are several scripts involved, but then you must decide which of those is the script, and the others are then other scripts. And that has the advantage that instead of having to provide the datum as built-in data, you can use the type that's appropriate for the script. So in our case, our datum type was unit, so we can just specify the datum here as writing unit. And the rest, I believe, is more or less identical to what we had earlier. Next, we could look at the playground to try it out, but I won't do this now because even though the implementation of the validator is different now using this typed version, the behavior from the point of view of the user, somebody interacting with the contract, is exactly the same as before. So it will look exactly the same as in the last example that we looked at in the playground. So in particular, if you provide the correct redeemer 42, you can unlock the gift, and if not, then validation will fail. So instead, let's look again at how this actually works and what has to be done in order to make this work. So the low-level underlying representation is something, as we saw before, that takes 3 built-in data arguments and produces a unit or throws an exception. But now we have something where the first 2 arguments can be of a more or less arbitrary type, and then the third one is script context, and we return a bool. So there must be some sort of translation, some back and forth. So basically underlying at validation, we get the datum and the redeemer and the script context in the form of built-in data. So then what this wrap, or rather this wrap validator does, it must first translate these 3 arguments that are all of type built-in data into these more high-level types. So it must convert the first built-in data, in this case, into a unit, the second one into an integer, and the third one into a script context. Then our custom logic is executed, which returns a true or false. And if it returns a true, that must then be translated into unit, the result that this low level expects. And if it returns false, then an exception must be thrown, or an error must be triggered, which is the behavior that the low level stuff expects in case validation should fail. So there must be this back and forth. And in particular, we must be able to translate built-in data into these types. So somehow, in this case, the compiler must know how to translate built-in data into unit or into integer and into script context. And how does that work? Well, there's a type class for it that we can look at. That is in module plutustx.isData.class. And actually, there are 2 type classes related to this. One is called toData, one is called fromData. And as the name suggests, an instance of class toData has this toBuiltIn data method that takes an A and returns built-in data, and something that is an instance of class fromData takes built-in data and tries to convert it into an A, which can fail. Then if you go further down in this module, you see, lots of predefined instances. So for example, unit and integer are instances of both fromData and toData. And we see there are like different versions as well. something called unsafe from data, which is unsafe as the name suggests, but more performant, and also functions that deal with data instead of built-in data. We can try this out in the REPL. For that, let's first import Plutus TX, and Plutus TX is data class. And we know that unit implements toData and fromData. So for example, we can do toData unit, and we see that unit as data is represented with this constr constructor 0 empty list. And to go the other way around, we can say fromData constr 0 empty list, and we must of course tell the compiler what type we expect. So we expect maybe unit, and indeed that succeeds, and we get just unit. So if instead we did something else, I don't know, for example 1 here, then we would get nothing. So that would not be the correct encoding of unit. Of course, unit is a bit boring. Let's try it with integer. So let's see toData 42. And not surprisingly, the I constructor is used in this case. So to go the other way around, that succeeds. But if we use a different constructor, for example, list, then that would be invalid. So the empty list would not be a valid encoding of an integer in the data or built-in data type. We can also ask for information on the, for example, toData class, or toData. And we see there are a couple of predefined instances. We also saw that in the header documentation that I showed you earlier. And this in particular explains why our example just worked, because there are instances for unit and for integer predefined. And you see a couple of other instances predefined. However, that's still not completely satisfactory if we would have to restrict ourselves to these types where there are already instances for toData. What we really want to do is use custom data types that are well suited for the problem at hand. And normally in a situation like that in Haskell, you would need to by hand write instances for toData or fromData if there is no predefined instance yet. However, luckily we normally don't have to do that by hand. There is an automatic mechanism provided by Plutus, and we'll look at that next. So finally, let's look at how to make custom data types work with isData and typed validators. So I copied the type module under the name isData, and let's say instead of integer for redeemer, we want a custom data type. Let's use a simple new type, my silly redeemer, which just wraps an integer. And let's try to replace the integer here, where we have the redeemer, with this type. So in order to pattern match, we can just pattern match against this. So R is now an integer again, so this should still be correct. Here in the type instances, we have to replace the integer with my silly redeemer. Okay, this should be fine. Here, my silly redeemer. So that should be it for the on-chain code. Now for the off-chain code, we must just in the grep instance where we give the redeemer, we must somehow now provide the right thing there. And actually we don't really know what to write there. So what we can do is toData of my silly redeemer are. So if we now try to load that module, we do get, okay, first we get the error that is ambiguous. Let's call it Plutus TX to data. Okay, typo. Okay, but now we get the error message that no instance of isData for this class, my silly redeemer. In order to fix that, we could write an instance for isData of my silly redeemer by hand, which in this case would be relatively straightforward because we could somehow reuse the one for integer. But we don't have to. Instead, we can use Plutus TX unstable make isData, which is again a function using template Haskell, like this. Let's first see whether it works. Yes, now it compiles. So this is a template Haskell function, and it takes a type. And the syntax to provide a type is to use 2 single quotes in front of the name of the type. And this will then, at compile time, write an instance for isData for this type and splice it in here at this point. So this is as if we manually at this position here in the source code had written an instance for isData. And now actually we should be able to try that out as well. So if we again import Plutus TX and Plutus TX isData class, and now do something like toData my silly redeemer 42, then it works. And we see it doesn't just what we might have expected, reuse the instance for integer. So in that case, it would just be I42, but it uses the constructor of the data class. So that's not obvious maybe, but that's how it's done. Okay, so, and this of course works for other custom types as well. So using this Plutus template Haskell function unstable make isData, we can turn custom data types into instances of isData and then use them in our validator scripts, in our typed validators. In case you're wondering why it's called unstable, there's also a stable version which you should use in production code. So this is about constructors. We saw that in this case, the my silly redeemer constructor was translated into constructor 0. I suppose if there's only one constructor for a data type, it will always be 0. But if there are several constructors, it's not so clear in how they are ordered. And the difference between the unstable and the stable version is that the unstable version does not make any guarantees that between different Plutus versions, the constructor number corresponding to a given constructor will be preserved. And that of course would be bad, because if you use an older version of Plutus to serialize something to data, and then a newer version of Plutus makes it in a different way, does that in a different way, then it would be incompatible and you would have round-trip problems. And if you use the stable version, then you can explicitly specify which constructor corresponds to which index. So then it's guaranteed to work between different versions of Plutus. But for now, for quick and dirty trying, I'll always use the unstable make isData. So let's quickly try this out in the playground, whether it still works as before. It should be exactly the same behavior. So I pasted the new code into the editor and compiled, and same scenario as before, first with the wrong redeemer. And yeah, we only get 2 transactions, and wallet 2 didn't successfully grab. Now let's provide the right redeemer and try again. Now we have 3 transactions, so the grab worked and the balances are also correct. So we see that both the untyped and the typed version behave exactly the same, but the typed version is much nicer to work with.